Hello, everyone. This is Dr. Lennon, and this is the beginning of lecture on 4.3 optimization. So this is what we'll be working on today and Tuesday, and then hopefully when I get back, so after Tuesday I get back, we'll go over this and continue with a few more examples. And then I plan to do limits and L'Hopital's rule after this. This fits in a little bit more with the derivative and, loosely uh, ties into implicit differentiation and some of the kind of first derivative stuff that we've gone over already. So I thought it would make more sense to introduce this section before we did 4.2. They aren't really super related. I mean, for doing L'Hopital's rule in 4.2 involves taking the derivative, but the sections are independent and don't necessarily rely on each other in any meaningful way. So I just want to go through two pretty basic examples and give you two to spend time to try on. And again, just kind of try and take notes. So the examples are very similar to the problems that I'll assign you at the end. And again, I'm not going to be grading the ones at the end, but I do expect you to try them and include those as part of your notes. And I will just check that for completion on Tuesday. All right, so let's get started with a definition and a theorem. So a definition, and I think I've used this terminology before, if f of x is just some function that's differentiable, if you have a point on an interval, so some value a such that the first derivative, I wrote the same thing here. That doesn't make any sense. So it should say f prime of a is equal to 0 or f prime of a is undefined. Almost all the time it's going to be f prime of a equals 0. But if we say f prime of a equals 0 or f prime of a is undefined, then we call a critical point of f. So after we get back, I'll make these notes available. But at least the lecture slide, but I want you to take notes on them just for the purposes of showing that you actually watched the video. And I will get that fixed. All right, so so we saw when we did lots of examples with graphs and stuff like that. So local minima and maxima will occur at these critical points typically if we find all the values where f prime of x is equal to 0 and then go ahead and test the regions around them, because we know that if the derivative is positive, then the function is increasing, and if the derivative is negative, then the function is decreasing. So if you change from increasing to decreasing, you get a max, and if you change from decreasing to increasing, you get a min. Okay, so there's something that's a little bit more specific, talking about global maxes and mins. So that's what the extreme value theorem here says. So if you have a continuous function on a closed interval, then the function will always achieve a global max and a global min on the closed interval. And the real important thing about that is it turns out that the global max and global min will only occur at either the endpoints of the function, either a or b, or any critical points in the middle. So essentially the steps we're going to use to solve problems in this is we're going to take the function, take the derivative of the function, set that equal to 0, and then solve that. So those will give candidate x values along with the endpoints that are the places where the function is going to have a global max and a global min. It's going to achieve both of these always on a closed interval, provided the function's continuous. So that's all you have to do is plug in those points and then compare the y values, because we're determining max and min based on which has the largest y value and which has the smallest y value. So let's look at a very concrete example. So find the maximum and minimum values of f of x of the function x over 2 plus sine of x on 0 to 3. So again, we have a continuous function. X over 2 is continuous everywhere. Sine of x is continuous everywhere. So if you add them, they're continuous everywhere. Therefore, they're going to be continuous on the closed interval from 0 to 3. Okay, so we're going to take the derivative, find any critical points, and then we're going to plug 0, 3, and any critical points into f of x and then compare them. So when we take the derivative, we get a half plus the cosine of x. We set that equal to 0 to try to find the critical points. So we end up with the cosine of x equals negative 1/2. So keep in mind that we're on the interval 0 to 3. So that's basically only between kind of like 0 and pi, almost right. 0 to 3.14 would be 0 to pi essentially. So there's only going to be one solution here. That's actually the principal value region for cosine. So we could just take inverse cosine on both sides, and the calculator should return the right answer because it's the principal value region. If it were another region, we'd have to, draw the picture and then, think a little bit harder. But in this case, it's pretty easy. We see that x is just going to be 2 pi over 3. So that's the solution there. So we're going to plug 0, 2 pi over 3, and 3 in. So I do that on this next slide. So plug them in, and we get the three y values: 0, 1.91, and 1.64. So that's going to make 0 the min. So the min, we say, occurs at x equals 0 and has value 0. So the min occurs at the x value and has value, whatever the y value happens to be. And the max is going to occur at 2 pi over 3, and it's going to have value 1.91. So that's what I said here. F assumes the minimum value of 0 at x equals 0 and its maximum value 1.91 at x equals 2 pi over 3. So again, we see, as we do many times, we're using the derivative of the function to actually give us information to tell us something more about the function. All right, next example is a word problem. This one's very basic, but you get the idea of how to set one up. So the one on the homework is a little trickier, but not too much. One like this is you could guess the answer, right? Because there's no conditions. Two non-negative sum to 10. How large can their product be? Probably you would guess 5 and 5 because, okay, those are the numbers that are closest together, and that's going to be the right answer. But really, we're going through this to see kind of how to set it up. So basically, we just use two letters, so we know x plus y equals 10, and then their product is x times y. So we call the thing that we're trying to maximize or minimize, that's typically known as the objective function. So we're always looking for two things: the objective function and the constraint on the word problem, because when we're working in Calc 1, essentially we're only dealing with single variables, which means we have to have the thing that we want to maximize. And in this case, we're using two letters to start out: x plus y equals 10. And then we are going to have to be able to substitute, so we get down to a single variable, and then we can take the derivative of that objective function once we've replaced using the constraint to narrow it to a single variable, and take the derivative. And again, we can think of this as an extreme value theorem problem, because if we think about two non-negative numbers summing to 10, you can basically think of those numbers falling in the range from 0 to 10 themselves. Especially if they say something like integers. Here they don't necessarily say integers. But, once the number is larger than 10, you'd have to have a negative in order for it to add to 10. So essentially, they have to fall between 0 and 10 in this example just because of non-negative. So, okay, so what do we know? We know the product that we're trying to maximize is x times y. So that's the objective function. And then the constraint is x plus y equals 10. So we plug that in first, and we see our product function can be written as x times 10 minus x. So we can multiply through, so 10x minus 2x, and then take the derivative. I use the Leibniz notation. So dp dx equals 10 minus 2x, and solving that implies that x is actually equal to 5. Again, the other ones, it doesn't make too much sense as a product, because if one of the numbers is 10, the other number is 0. So that product would be 0. So we see that the maximum product here is just 5 times 5 when both of them are equal to 5. So a pretty straightforward problem, but really that's why you're looking for the objective function and then the constraint. So a lot of times the constraint, when these problems get hard, again, it's usually not because the calculus is the problem. That's because the constraint can come from somewhere funny in older math topics. So say something like similar triangles or Pythagorean theorem or any number of things, but the constraint might not necessarily be explicitly stated. It could come from some convention in geometry or even a picture, or you could have an objective function and then just a constraint equation that's given to you based on any number of things. But you're always looking for those two, and then finding a way to put them together to reduce your variable count to 1. All right, so the two problems I want you to work on that I will also like to see an honest effort for is this first one. Find the absolute extreme points for the function f of x equals 2 times e to the 0.5x plus e to the negative x on negative 1 to 2. Again, you can't solve this one by hand, so it just requires a little algebra. It's not so difficult. You just need to remember the derivative rule for e to the kx is k times e to the kx. And that should be enough to get you started. And, take the derivative, set it equal to 0, find your critical points. Again, this one, nothing too much to worry about because all of your, you're never going to have a undefined value for f prime of x because the domain's going to be all real numbers. For the second one, we have the sum of 3 non-negative numbers is 36. Okay, so typically that would be 3 letters, x plus y plus z. But then we're given that one of the numbers is twice as large as one of the others. So what's the maximum value of the product of these 3 numbers? So basically, again, we've got a product. In this case, you might say, okay, x times y times z. But again, you could set one of the numbers, say, z equal to 2 times y. So you really only have 2 letters to start. You have an x, a y, and a 2y. And then you also have the other constraint that when you add them all together, you get 36. So your product, you can start with x times y times z equals your product p. And then you kind of have 2 constraints here that you can put together in 2 steps. So essentially, z is equal to 2 times y, and then when you add them all together, you get 36. So when you put those 2 things together, you should be able to reduce your product function to a single letter, say just x. Again, then you're going to take the derivative and solve. So again, this is an extreme value theorem example because we're adding 3 non-negative numbers. So they have a very restricted range, right? The range of values has to be between 0 and 36. So you have those 2 endpoints, and then you have the critical point. So that's going to have to attain global max and global min. You can test all 3 values, but probably when you plug in 0, you're going to get 0 like we did on example 2. All right, so that's it. Hopefully that makes sense. If it doesn't, we'll go over any problems you might have had on Tuesday, and I'll get another one of these set up on Wednesday. All right, this is Dr. Lennon signing off.